sessions from the schools of crop improvement and crop protection. I now take the proud privilege of welcoming the dignitaries on the dais. Esteemed Chairman of the session, Professor R.B. Singh, former Chancellor, Central Agricultural University, Imphal. Director, Dr. A.K. Singh, and Dr. Rashmi Agarwal, Dean and Joint Director Education, IARI, Dr. Neera Singh, convener of the sessions on the professor's presentation. Welcome you all. May I now request Dr. Rashmi Agarwal, Dean and Joint Director Education, to kindly present formal welcome address.
Thank you. Good morning, all of you. It is my pleasure and proud privilege to extend a very warm welcome to all of you in this auditorium on the second day of our Convocation Week program. This, as you know, this is 58th Convocation of IARI, and as said that we have presentations of the significant achievements of the students will be given by the professors of individual discipline in the school mode. So this morning session, there will be two schools. First is a School of Crop Improvement, followed by the School of Crop Protection. So on this occasion, I would like to welcome Professor R.B. Singh, who will be the chairing the first session of School of Crop Improvement. Professor R.B. Singh, sir, we are very thankful to you for accepting our invitation and chairing this session. None other than you will be the most suitable chairperson to guide the students' research and listen to all the students' significant research contributions presented by Dr. Vinod for genetics and plant breeding, and Dr. S.K. Jain for seed science and technology, and plant genetic resources by Dr. Veena Gupta. Sir, I welcome you, sir, on this occasion. I would also like to welcome our director, Dr. A.K. Singh, on behalf of PG School and on my own behalf. Sir, we welcome you, and we hope that you will be there throughout this session. Because he is so hard pressed with so many other engagements. This significant students' research is a reflection of overall research of Indian Agriculture Research Institute. As I mentioned earlier, the student research is an integral part of the activities of IARI, and last year more than 300 publications have come out of the students' thesis work, including MSc and PhD, and more than 50%, roughly 170 publications were having NAS rating more than 6, and maximum NAS rated paper was of 13.91. So on the first session, we have invited the professors of the discipline, as I said earlier, of the crop improvement, and their presentations will be largely based on the theses which are submitted this year and the students who will be getting degrees for MSc and PhD program. So the chairperson of today's function are Dr. Professor icon in field of agriculture in general and genetics and plant breeding in particular. Now I would like to request our director, Dr. A.K. Singh, to welcome Professor R.B. Singh with a bouquet of flowers. Now it is the time to introduce our chairperson of today's session. I would like to request Dr. A.K. Singh to kindly introduce the chairperson of this session. Thank you.
Very good morning to each one of you, and thanks for being present in large number. Professor R.B. Singh is known to become ASRB chairman. Again back to FAO as Assistant Director General, which is again a very prestigious position for an Indian to get. On coming back, he became a member, Farmers Commission. And then after that, as President, National Academy of Agricultural Sciences, and the Chancellor of Central Agriculture University, Imphal. And is a fellow of all the science academy in the country, and decorated with the most coveted Padma Bhushan, the highest civilian award in the country. It is our indeed a great pleasure, sir, to have you here, and we would look forward to listen your advice, your inspiring words after the presentation is over, and we will be greatly benefited. Thank you very much.
May I now request Dr. Neera Singh to kindly take over the session and conduct further proceedings.
Very good morning, everyone. Respected Chairman of the session, Professor R.B. Singh, Director IARI, Dr. A.K. Singh, Dean Madam, Dr. Rashmi Agarwal, dignitaries of the dais, Head of the divisions, professors, scientists, and dear students. I welcome you all to the day 2 of the Convocation Week program. And as Madam earlier told you, today we are starting with the academic achievement of the students, and we are presenting it in a school mode. So total there are 6 schools, and today is the School of Crop Improvement. Total 31 theses will be presented in this session, including 20 MSc and 11 PhD. Professor Vinod, Professor Veena Gupta, and Professor S.K. Jain will be presenting on behalf of genetics, PGR, and seed science and technology. Just to brief, we have already allocated time to each professor depending upon the time available in session and number of PhD and MSc thesis. So 2 minutes before the time end, I will just switch on, give you an indication and switch on the yellow light, and after 2 minutes, red light will be lighting, and I expect each one of you will be honoring the time allocated to you so that we can finish the proceeding of the day in time. So I request Professor R.B. Singh to start the proceedings. Thank you.
Thank you, Neera. Good morning to each one of you, ladies and gentlemen. I must thank Professor Ashok Kumar Singh, the director of the Institute, for his kind words and introduction. Rashmi, so kind of you, and of course Neera on the left and right, the colleagues who are helping in this deliberation. Friends, there is something called undiminished pleasure and privilege. It ever enhances. It's a nostalgic feeling to be in IARI campus for me. It is more than a home for me, and therefore it's always so delightful to be with you, my colleagues here in the front, and of course the future of India, the outstanding students from all over the country. And this is a mini India. When I really come to campus, I start feeling I have the feel of the mini India. And each one of you, the way you contribute, the message goes. IRI is not just any other institution. IRI is the institution to lead the welfare of the largest humanity in the world. And this is what you are. Your responsibilities are there, and this is how you perform. So I'm very proud of each one of you who are here, and of course your presentations will enrich it further. My effort at the moment will be just to listen to you, and Neera has been very strict. She has the light control, so please speakers, kindly make your points straight. Don't have to go in too much detail so that we finish it in time, and give me 2 minutes to sum up if I may, and then we break in time, so that because this total week is full of events, one session, the other session, all sessions, and so on. And I was just envying Rashmi that how do you keep up with all this? She has to be present all over. So I sympathize with you and with the director, of course, and each one of you who are concerned with this. But then I feel happy in a way because I have gone through this process for 6 years here at this institute. So I am quite familiar what it means and the way you take the responsibilities. Thank you very much. And then Neera, now it is that we can call the, the first speaker, Professor Vinod. Of course, in the papers you have been shown to get 40 minutes to make your presentation on genetics and plant breeding, but I hope as brief as you could be, and I'm sure you can summarize things quickly. So, Vinod, please kindly, yeah, you are here and we'll listen to him.
Respected Professor R.B. Singh, Chairperson of today's session, Dr. A.K. Singh, Director IARI, Dr. Rashmi Agarwal, Dean and Joint Director Education, Professor Neera Singh, Convener of the session, heads and professors and all faculty members and dear students. So I am making this presentation on behalf of the students of Genetics Division. So this is the mandate of the Genetics Division. If you see, the mandate includes basic and strategic research and of course applied research, and then the other things. So all our students, they work according to the mandate of the division, and you will find that everyone is working in the given mandate of the division. And this is a brief introduction about the faculty. We are having a total of 64 faculty members. Out of 64, 55 are from IARI, and 9 are from other regional stations or from sister institutes. And this year, 19 students are presenting. I will be presenting the work of 19 students. They will be getting degree this convocation, and out of these 19, mostly almost 70%, 13 are from the MSc students actually, and 6 are PhD students. And the areas are basically which we have covered in this presentation are biotic stresses, abiotic stress tolerance, improvement in quality traits, and certain areas which are miscellaneous I have grouped together. And then crops are wheat, rice, maize, lentils, soybean, chickpea. Of course, some of the omissions you will find this year is that we don't have brassica presentation here, and pearl millet also, because students, they have not submitted this year. They are going to submit, so maybe next year we will include those presentations. And these are the students who will be getting degree, and they have contributed in these presentations. So 13 are MSc students and 6 are PhD students. And I will start from biotic stresses. And all of you know, wheat is an important crop, and it's affected by many diseases. And among the diseases, rust are the probably most important globally. And this work was taken by MSc student, and there is a synthetic variety, synthetic wheat genotype, synthetic 55. And our earlier student identified rust-resistant genes in this variety, in this genotype. And this student worked to see the effectiveness of this gene, and also to determine the identity of this gene with either pathotyping or with allelic test of allelism. And this is the materials you can see here. What he used is that he made crosses to study genetics, and then he used several genes. The gene was located in chromosome 1D, so other genes which are located in chromosome 1D, test of alleles was done, and conclusion was made based on the results. And the important conclusion was that the gene, leaf rust resistant gene in the synthetic 55 is probably a potentially novel gene, is a new gene. It's not LR21, it is not LR66, and it is different from synthetic 45 genes. So potentially we have students have identified a new gene. So that's very important, I think, discovery. And this is actually a continuation of the work of two MSc students. So I think we may have a combined publication from this work, and definitely now we have done additional work also after this, and we are sure it's a new leaf rust resistant gene. And continuing in the same area, leaf rust resistance, another student worked on NP series, dicocum. Now, dicocum is a tetraploid wheat. It is also known as couplet wheat. And the idea was again to see the effectiveness and to determine the identity of the gene. And this gene is very effective. It was tested against 21 leaf rust pathotypes, and it showed resistance against against all the 21 pathotypes. And the 3 dicocum genotypes were taken: NP200, NP201, and NP202. And it was observed that these 3 genotypes, they carry a single recessive gene. So rust resistance in all these 3 genotypes is controlled by a single recessive gene. And then test of allelism and other pathotyping tests. With that, we concluded that all the 3 genotypes, NP200, 201, and 202, they carry the same leaf resistance gene. So all the varieties, all these genotypes, they carry actually same resistance gene. So resistance is the same. It's a recessive gene, and now in future we can take up mapping of this gene. This is also potentially a new gene. And this is the same finding. You can see the effectiveness of the gene. And then another student continued work on rust resistance in wheat, and again an MSc student. And this couplet 72 is again a dicocum genotype. So couplet is a tetraploid. It is dicocum, and it is cultivated in a significant part of South India. So, and the idea was to see the effectiveness of the gene which is present in couplet 72, and then to study the genetics and to identify molecular markers, putative markers which are linked to resistance gene. And if you see here, the gene showed effectiveness against almost all the pathotypes which we used in this study. So it's a highly effective resistance gene. And then genetics we worked out, and it was found a little bit more complex. It was we got 13:3 ratio in F2, and probably there is one dominant gene and one recessive gene. So rust resistance in couplet 72 is controlled by 2 genes, one dominant and one recessive, and so that's created a problem in mapping of the gene. But BSA student was able to do BSA and identify the 2 genes, 2 chromosomes 6AL and 6BL, and which showed polymorphism and probably linked with resistance gene. But of course, this requires further work to determine the identity and develop markers for this gene. And then coming to abiotic stresses in the wheat, MSc student Manjunatha, he worked on morphological molecular characterization of wheat germplasm for drought and heat tolerance. And so student Manjunatha worked on drought and heat tolerance, and again an MSc student. And objectives were to morphophysiological and molecular characterization of wheat germplasm and validation of molecular markers linked to QTLs for heat and drought tolerance. And these were the traits which were for which phenotyping was done. And you can see here phenotyping was done in 2018 as well as in 2019 in irrigated condition, in red-wet conditions, late sown conditions. And then based on the QTLs diversity, identified QTLs, allelic diversity was studied, and these were grouped into 2 groups. So basically all the genotypes, they fell into 2 groups. One was from that's Indian genotypes, and other from exotic, either Semite or Australian genotypes. And this is how the different genotypes they grouped here. And then some of the markers, already reported QTLs, they were validated in these lines. A number of QTLs, you can see here, they were validated in this study. So these are useful QTLs, and these can be used in our crop improvement program. And then continuing the abiotic stress tolerance, work was undertaken for drought tolerance in wheat. And here the strategy used was backcross inbred lines. And these were phenotyped for drought tolerance, and then QTL mapping was undertaken. And in this phenotyping was done at Delhi, Indore, and Pawarkheda at 3 locations, and 2016 and 17 and 17, 18, 2 years. So it was multi-location, multi-year phenotyping, and a number of traits were taken: NDVI, CT, chlorophyll content, relative water content, And then genotyping was done using both SNP and SSR markers. And then map was developed and QTL analysis was undertaken. And salient findings are that 77 QTLs were detected, and out of these 77, 10 QTLs had more than 10% phenotypic variance. So these are maybe important QTLs which can be useful. And on chromosome 2A and chromosome 5A, multiple QTLs for drought-related traits were identified. So probably these are having these regions are hotspot for drought tolerance QTLs. And then abiotic stresses were continued in rice also for drought tolerance. And our student Manoranjan Senapati, he worked on drought tolerance in rice, and the emphasis was on root system response under drought situation. And again, the effort was made to map the genomic regions associated with drought associated root system traits in rice, and then validation of some of the QTLs was also undertaken. So this is how the various traits were phenotyped, and then correlations were worked out, and you can see some of the correlations were significant. And then genotyping, actually information was already available. So student did not do this information was already available, and only phenotyping was done, and then the association mapping was undertaken, and you can see on different chromosome significant trait association were found. These are the markers which are linked with different traits. And if you see, these are the markers which were identified in this study, and they showed the association with the drought-related traits, and of course some in silico analysis was undertaken, and candidate genes were identified present in these genes in these regions, and these carried these genes are having known functions with drought tolerance and with root-related traits. And then some of the markers, some of the QTLs were validated in this study, and 3 QTLs were validated, that RDW, that is root dry weight, shoot length, and shoot dry weight. So all these earlier reported QTLs were studied in this present study. And then same abiotic stress work on abiotic stress tolerance continued in soybean also, and the student Srinivasa, he worked on the drought tolerance traits in soybean. And the idea was to screen the soybean genome for drought tolerance and to study the inheritance of drought tolerance in soybean, and then mapping of drought tolerance genes. And if you can see here, 328 lines were screened for drought tolerance. Out of these 328 lines, 75 lines were finally used for phenotyping under hydroponic conditions. And genotypes were identified which showed good drought tolerance, and finally mapping was undertaken in you can see here in F1 and F2 generations, and in the results based on hydroponics was that it's under control of a single gene. So one gene was identified for drought tolerance. Of course, it's sometimes it sounds, because drought tolerance is very often we say it's complex trait, but here we got a single gene which is responsible for drought tolerance here, and this study is under hydroponics actually. And then QTLs were also identified. Set 77, this QTL is linked with drought tolerance, and the distance is about 3.2 centimorgan. And on similar lines, work was undertaken in soybean on salinity tolerance also. So here the experiment was again conducted under hydroponic conditions, and genotypes were screened for salt tolerance, and then study of inheritance was undertaken, and mapping attempt was made to map the genes. And here you see 82 genotypes were screened, and this is the genotype Abira, FT Abira, which is known for drought for salinity tolerance in case of soybean, and PUSA 9712 was identified as a tolerant genotype in soybean in this present study. And then attempt was made to map the gene, but when cross was made between Abira and PUSA 9712, it was observed that all the markers which were present in Abira and which are linked to salinity tolerance, they were monomorphic. So it was concluded that the same gene and QTLs which are responsible for salinity tolerance in Abira, they are controlling this, they are present in this line also, and this line can be a good source of salinity tolerance in soybean. And of course, studies were made, you can see here, this is the genotype which was identified as salinity tolerance, and it showed very good germination, 100% germination, where other genotypes, they fail to germinate under saline conditions. And then coming to nutrients, improvement in nutritional quality, of crops, work was undertaken in case of lentil, and it was related with the nutritional quality parameters. And nutrition is actually very important. Now from food security we are moving to nutritional security, and you will see in coming slides that a lot of good work is being done in improving the nutritional quality of various crops. So this is the crop lentil where a PhD student undertook this work, and screening of objectives were to screen the diverse lentil genotypes for grain nutritional quality parameters, study of genotype and environmental interactions, molecular characterization of the lentil genotypes, and association analysis. So if you see here, these are the traits which were undertaken by the students: iron and zinc, then protein content, antioxidants, flavonoids, phenols, and phytic acid concentrations. So number of traits were phenotyped, and again crop were raised at different locations: New Delhi, Sagar in MP, and Sihar. So under multi-location conditions, these traits were evaluated, and finding was that for these quality traits, a lot of variability was observed. You can see here for protein content, it was 18 to 27%, and similarly, a lot of variability was observed for grain iron and zinc, and also for phenol and other antioxidants. So, and then marker trait association were undertaken, and markers were identified which were linked with these important quality traits. And if you see here, the R square value is quite significant. So I think important criterials and markers were identified in this study. And this is a work undertaken in maize to improve the vitamin E content in maize. In fact, our maize group is doing excellent work in improving the nutritional quality. And this work, yesterday the student was selected for IARI merit medal, gold medal. So this is an are actually compounds which are vitamin E, constitute vitamin E, and in tocopherol they are alpha tocopherol, beta tocopherol, and delta and gamma tocopherol. But the alpha tocopherol is the most efficient, and then the student worked to improve the quality of to improve the quantity of alpha tocopherol in maize. And if you see here, these are the different genotypic classes. In fact, if you see the gene VTE4 gene, if we see the haplotype of the gene, there are two regions where there are insertions or deletions, and here is 0, 0 means both the regions there is no insertion, and here there is 118 base pair insertion, and here there is no insertion. And at this location there is no insertion, and here 7 base pair insertion. Again 18 insertion and 7 base pair insertion. So this haplotype, based on this haplotype, genotypes can be classified in different categories. And if you see here, this 0, 0 category, this is alpha tocopherol is high, and as you move towards this category, alpha tocopherol content goes down. So this is the favorable allele. We have to select for genotypes which are having this favorable allele. And here you see this is the haplotype 0, 0, and this is 7, 1, 8. You see the contrast here. Here alpha tocopherol is 37%, and here it is only 21%. And here also this has come from 65 and 52. So this is the total tocopherol content, but here important is that alpha tocopherol is much higher in this when this allele is present, and alpha tocopherol content is lower with this kind of allele if present in genotype. And these are the 4 hybrids, released hybrids. These are QPM hybrids, and these are the parental lines of these hybrids. So what a student did, he improved these parental lines of these hybrids for vitamin E content. And the donor parent was a genotype SEMI25, and using this genotype, marker state breeding was undertaken, and you can see here there is significant increase in alpha tocopherol. Almost twofold increase is there in most of the cases. So alpha tocopherol content was increased in by marker state backcross breeding, and so these genotypes are very important, and because these are inbred lines of released hybrids, so these hybrids can be reconstituted, and we can have enriched hybrids which are enriched for alpha tocopherol. And continuing the same work, in fact there is a lot of synergy among different students. The one student worked on the development of inbred lines, development of inbred lines for alpha tocopherol, and another student characterized these lines. So this student, Mr. Manoj Gowda, he worked to characterize the mass derived. Now these lines carried genes for favorable allele for this vitamin E, alpha tocopherol, then CRT RB1 and LCYE. These genes are responsible for beta carotene and then OPEC2. So these are the lines which are enriched for protein, quality protein. These are enriched for beta carotene, provitamin A, and also vitamin E. So, and these inbreds were characterized, hybrids were characterized, and of course multiplex PCR was also developed by the student. So just if we go into this table, we can find that these are the 4 inbred lines, and this is very important. If you see here, this is the line which having a provitamin A, and if you see alpha tocopherol, it is 9 here, and all these lines in which PV which have been fortified with vitamin E, you see there is almost a 2-fold increase. From 9 it has gone to 17, 17.5, and at the same time provitamin A content and lysine and tryptophan content, they have remained more or less same. So there is no, so if you see these lines, this is fortified for alpha tocopherol, fortified for provitamin A, fortified for lysine and tryptophan. So these are very important lines as far as nutrition quality is concerned, and all the 4 inbred lines we are having these fortified lines, and these can be then used, and these were characterized for this. You can see most of these lines, they are similar to recurrent parent, and only few traits they differ for few traits, and these traits were deliberately selected for the for the purpose of varietal identification. And here you can see the hybrids were reconstituted, and the same story was repeated here. What we got in inbred lines, similarly similar concentrations we got in reconstituted hybrids. So these are ready-made hybrids. Actually, inbreds we are having which have been fortified for alpha tocopherol, provitamin A, for lysine, tryptophan, and they are having comparable yield. So these hybrids have shown good results, and I think these are as far as nutritional quality is concerned, very important material has been developed by MSc and PhD students. And then for different genes, we have developed a multiplex assay that saves a lot of time. So for different genes, we have to do different single uniplex assays, but now with this multiplexing, we can save a lot of time and cost of genotyping. And now coming to continuing in MAGE, and again the provitamin A. This is the MSc student, and he worked on provitamin A and this MAGE. These are the lines which are CRT RB1 based lines, and these lines are rich in provitamin A. And if you see here these inbred lines, you see beta carotene content, it is 8.72, and here it is non-pro A line 2.34. So there is significant increase, a 3 to 4-fold increase in provitamin A. So then similarly, you can see other carotenoids, and there is significant increase in these carotenoids in provitamin A and these lines. And this clustering was undertaken using some of the molecular markers for CRT-RB1 based genotypes, and here you can see the hybrids. Actually these are the hybrids which are developed using those inbred lines, and they are rich in provitamin A, and at the same time they are having good yield. And these are the in fact hybrids developed from inbred lines which were developed at IARI. So these are not these are new lines, and these are available in our MAGE section, and so they are very important material, and hybrids can maybe in future we may come up with these hybrids. And then another student, he worked on from coming to nutritional traits to baby corn, because baby corn is nowadays becoming very important. If you see in most of the supermarkets, you will find baby corns, and one idea was to develop baby corn hybrids using cytoplasmic male sterility, so that there is no pollination and the quality is improved. So just to develop good quality male sterile hybrids, some of the inbred lines were selected, and these are the fertile inbreds, and then 3 cytoplasms were selected: CMST, CMSC, and CMSS. So all these lines were converted into 3 different cytoplasms, and so these are alloplasmic lines, and then these were characterized with 40 mitochondrial SSRs, and then one this marker FHMT189 was identified, which was able to differentiate fertile cytoplasm and male sterile cytoplasm. And 7 markers they were able to differentiate among the 3 cytoplasms, but this marker was able to differentiate between fertile and sterile cytoplasm. So this is an important marker, FHMT189, and then effect of cytoplasm on fertility was studied, and you see here these are the hybrids, and these are the parental lines here, and these were converted into CMS lines, and then CMST cytoplasm. See, there no anther accession was observed here, and complete sterility was there. Similarly, CMSC complete sterility was observed only in few cases, and in case of CMSS, mostly fertility was there. So it was concluded that CMST T cytoplasm or Texas cytoplasm is the best cytoplasm as far as fertility is concerned. And then using these inbred lines, hybrids were constituted, and these hybrids are male style hybrids actually. If you see the two parents, after the two parents, one parent is having male style inbred, other parent is a normal line without fertility restoration gene, so that hybrid is also male style. So these male style hybrids were then characterized for different traits, and conclusion was that male style based baby corn hybrids with high yield quality were identified. So some of the important hybrids were identified which were good in quality traits for baby corn and also had high yield. And because these are male sterile, so they definitely possess better quality. There are no chances of pollination. So this is, I think, important piece of work as far as baby corn, which are becoming important nowadays. And then coming to rice, again, near isogenic lines were developed in rice for fertility restoration gene, and genetic analysis was undertaken. And if we see here, these are the lines, fertility restored lines, and these carried with the help of marker genes were identified. So the genetic constitution is RF3 and RF4 here, and this line carried only single gene, RF4. And this restored lines carry RF3, and then check was used PRS10, which carried RF3 and RF4. And these are the markers which are used for identification of RF3 and RF4 genes. And the conclusion was that in terms of efficiency of fertility restoration against wild abortive cytoplasm, RF4 is much more efficient in diverse genetic background as compared to RF3. So this was an important conclusion from this study, and it was also observed that in clean genetic background, in near isogenic lines, there is no significant difference between the RF3 and RF4. So RF3 and RF4 are equally effective, but in different genetic backgrounds, RF4 is much more efficient in restoring the fertility. And again, student work on rice on genetics of grain number, and this is he selected new plant type in rice, which is basically Japonica based material, NPT, and they have high grain number. So idea was to study the genetics of grain number and then to identify QTLs here. And if you see here, the F2 genetic analysis was undertaken in F2, and it was observed that it is by and large polygenic traits. You can see a normal distribution, and the population size was also very good. 977 F2 plants were phenotyped, and then grain number varied from 81 to 505. So a lot of variation was there in number of grains per panicle. And then mapping was undertaken on only one marker, RM424 was identified, which was linked with the grain number, and this marker was actually at 27.4 centimorgan from the trait. But this important thing that this is an MSc work and students do not have much of time, and important marker was identified. And future, I think we can undertake further work and saturate this region to identify closely linked markers. And then one of our student, she is from Myanmar, and she worked here, and she worked with Dr. Gopal Krishnan, and there is a mutant actually here. M507, this is a mutant in Nagina 22, and this shows stripes in leaf. So this is leaf stripe mutant, and the genetics of this mutant was studied. And of course here you can see chlorophyll content was observed, was estimated, and there was reduction in chlorophyll content in this mutant. And mapping was undertaken here. So genetic analysis was done and mapping was undertaken. So if you see here genetic analysis, it was 13:3 ratio which was observed in F2, and the student concluded that the trait is governed by two genes interacting in inhibitory epistatic manner. And of course these were two genes, but they tried to map the gene. And you see here the genes were two genes were mapped using two different BSAs, BSA1 and BSA2, and both the genes were located on chromosome 5, and markers, linked markers were identified. And then lodging is an important trait, is an important for in all the crops, and the lodging genetics of lodging resistance was undertaken in case of chickpea. So here the student analyzed 412 chickpea germplasms for lodging resistance, and he identified genotypes which are highly tolerant to lodging resistance, and the genotypes which are susceptible to lodging, they are prone to lodging. And then genetic analysis was undertaken, and here if you see here, these are the parents, susceptible parent, and this is a parent which is showing tolerance to lodging. And then in F2, a ratio 15:1 ratio was observed, and it was concluded there are two genes which are responsible for lodging resistance in this particular genotype, and these two genes were designated as SB1 and SB2. So these two dominant genes confer lodging resistance in this particular genotype, which shows lodging resistance. And then another important thing was that lignin content was identified to be positively correlated with lodging resistance. So genotype which had lodging resistance, they had higher content of lignin content, so this was related with, this was associated with high lodging resistance or tolerance. And then some work was undertaken by MSc student for genetic variability and stability analysis for specifically kernel size and kernel weight traits in tropical maize genotypes. And if you see here, the study was undertaken under 3 different environments. 2 were in Delhi and 1 in Dharwad. And then molecular profiling of these genotypes was undertaken, and they were clustered in different groups based on morphological as well as molecular markers. And then some of these genotypes which show stable performance across different environments were identified, and some of the genotypes were specific to environment. So these genotypes can be useful in breeding program, because they show stability for kernel trait, different traits which are related to kernel size and kernel weight. And then one of the students worked on soybean, and soybean there is a problem of seed viability. So after, if you store under ambient conditions, it rapidly loses its viability. So that's an important study, and our students have been working for quite some time on this particular aspect. And phenotyping and molecular characterization of interspecific alleles for mapping seed viability in soybean. This is the research problem which was undertaken by Mr. Ashish Kumar. And objectives were to characterize the seed for interspecific alleles for structural features and viability, and to map QTLs for seed viability. And here 217 drills were used, and 506 SSR markers were taken. And important thing is that this population is derived from interspecific rows, Glycine Souza and Glycine Max. And then studies were undertaken. Seed sample was stored at room temperature. Samples were taken after 1 and 2 years, and viability was tested. And then seed course structure, permeability, seed size, and various other traits were studied. And the results are that seed viability decreased over period of ambient storage. Some were faster than others in loss of viability. Permeability increased with time. It was positively correlated with viability loss. And poor storing genotypes developed cracks in hilum during storage, and seed storage appeared to be negatively correlated with seed viability. And then 24 lines with more than 80% viability after 2 years of storage were identified. And then the QTL analysis was undertaken for seed viability, and these were the 2 QTLs which were identified for 1 year of storage and or 2 years of storage. And you can see these are the linkage groups on which these QTLs have been identified, and they have they are significant actually QTLs showing more than almost 12% or 11% phenotypic variance. So this is about the research work which have been undertaken by our students. Total 19 students worked for this presentation. And coming to awards to the faculty, Dr. A.K. Singh was elected National INSA Fellow in 2019, and our young scientist, Dr. Gyan Prakash Mishra, he became NASA Associate in 2019. And then Dr. A.K. Singh, one of our faculty members, he became Director IARI. So I think this is a this is, I consider it's a big recognition for genetics faculty, sir. He is our faculty member, he was our head, and now he's Director IARI. So this is a big recognition, and I hope we will do much better under his leadership and guidance. So we expect a lot of guidance, and we hope to do well in coming years. And then some new faculty members were inducted, you can see here, and a total 32 research papers were published by students, not from exactly these students. Those even, I included those which were submitted last year also, because publications came afterwards. And the journals were, important journals are Plant Breeding, Euphytica, 3 Biotech, all these are important journals. So good publications came out from students. I hope many more will be coming in this year or maybe next year, because there is always some time lag in publishing papers. And this is regarding placement of students. Most of our students are well placed. MS students are doing PhD, and many of them have joined ARS. So all the students are well placed as far as they are concerned. And now I thank you all of you for your patience.